So in the last lecture, I talked about the natural sciences, and in this one, I want to turn to the formal sciences. As some of you may know, this is actually where I started my philosophical career. I was a mathematician, and then when I turned to the history and philosophy of science, I turned to the history and philosophy of mathematics. So I feel as though in this lecture, I'm sort of going home, and I'm trying to take stock of the views that I had 50 years ago, something like that, which I am trying to renew in somewhat different ways. So here we go. I think there are two myths that people widely subscribe to. The first is that logic and mathematics are known, or at least knowable a priori. And the second is that logic and mathematics describe some sort of abstract, non-physical realm. And one of the things I want to do in this lecture is to try to debunk these myths. And I want to do it by suggesting a rival account, one that gives progress in mathematics and progress in logic a major and central role. So I will outline right at the beginning a pragmatist alternative. Mathematics, I think, is a set of non-descriptive language games progressively generated from attempts to answer significant questions. Significant questions, remember, are the ways in which people come to diagnose what's problematic out of problematic situations. And logic, I think, informal and formal, is also comprised of non-descriptive languages progressively generated from human attempts to investigate the physical and social worlds. It's an interesting question to know which has primacy there, whether it's logic in the context of sorting out human disagreements, or whether it's logic in the context of trying to figure out how you do inquiry into factual matters. Now, I'll start with the myth of the a priori. Many philosophers, and this has been true, this is true today, it was true 50 years ago, are inclined to declare their favorite principles to be a priori. The term a priori is used incredibly loosely. And I don't know how many journal articles I've read in which somebody puts forward a principle and says, this is a priori. And I often think that what that means is, this is something I don't know how to justify in any way, but I'm really convinced it's true. And that seems to me an extremely unfortunate practice. And one of my philosophical heroes, even though I disagree with him on all sorts of things, is Kant. Kant is careful, intellectually responsible, where I think many later philosophers are inclined to go for the benefits of theft over honest toil. Kant's conception of the a priori, and I wrote a paper 40 years ago trying to work this out, is epistemological, I think. Kant talks about a priori knowledge, knowledge that's independent of experience. And I take that to be knowledge produced by a process of a type that would have been available given any experience that would have enabled the subject to have the relevant concepts, and a process that would always have produced warranted true belief. Now, it turns out that those three conditions are very strong, and they doom all sorts of putative a priori knowledge. And my critics sometimes describe them as absurdly strong, and with some justice, they saw this account of a priori knowledge as the effort of a vulgar empiricist who wanted to subvert the useful notion of the a priori. And so they said, well, how do we weaken this? Well, we allow for defeasible a priori knowledge. The process doesn't always have to warrant belief, and it doesn't always have to produce true belief. So a priori knowledge is knowledge just obtainable by a type of process that would be available given any experience capable of generating the pertinent concepts. A priori knowledge is what you can do in your armchair. And like other forms of knowledge, it's revisable sometimes, it's defeasible. Well, there's a different and much weaker concept. And that, of course, is not so easy to debunk. But I have some concerns about it. There you are, sitting in your armchair, and you're fully aware that a priori knowledge is defeasible. And you say, oh, well, this process, I don't really know much about what this process is, generates in me a firm belief that P. But you know that a priori knowledge is defeasible, and you don't have any particularly good ways of scrutinizing the process because it's so inchoately described when you try to describe it. Shouldn't you get up and maybe take a look, do some investigation? Isn't it a bit irresponsible just to sit there in your armchair generating beliefs in this way? Shouldn't we be rather unconfident about such beliefs? Quite contrary to the way people feel, say, about mathematics and logic. I want to diagnose the a priori. I want to give an explanation for why I think philosophers have come to believe that some bits of knowledge are available just by thinking. And this really goes back to some insights, I think, of Quine's. Certain propositions appear obvious to us. It's hard for us to imagine how they could be false, but as Quine pointed out, the history of inquiry shows the limits of the human imagination. And it also shows how some knowledge gets made obvious. And a classic way of making knowledge obvious is to jigger your language in such a way that it follows from the rules, the semantic rules for the language, that the sentence that you utter or write down is true. Quine pointed out, I think brilliantly, in Truth by Convention and then again in Two Dogmas of Empiricism, that that doesn't guard you against revision, that that's a sort of move that has at its back a prior history that shows that speaking a language or writing a language of that sort is a good one for your purposes. That's where Quine's residual pragmatism, I think, really becomes evident. So I think history matters. With respect to logic and mathematics, the most plausible candidates for a priori status, we tend to forget the history behind our beliefs. And as I mentioned, when I began philosophy, I began in the history and philosophy of mathematics, not just in the philosophy of mathematics. Our current beliefs have emerged from traditions in which many different ideas have been proposed and accepted. The progress of those traditions consisted in retaining the valuable ideas and in making them appear obvious. So let's look at mathematical truth for a moment. Should we understand mathematical truth by thinking of it in terms of Tarski's version of the correspondence theory? Paul Ben Asraf's seminal paper said, yes, of course we should. Are mathematical statements then true in virtue of referential relations to parts of reality? What would that reality have to be like? There are troubles, I think, with this view. The history of mathematics seems to show progress as new truths are added to the existing corpus of mathematics, and sometimes when old things that people used to write down are deleted. Can that really be seen as a series of episodes in which new parts of mathematical reality get to be discovered? Well, let's look. Discovery in mathematics, when you look at it closely, seems rather different from discovery in the natural sciences, and that shows up in the explanations historians give. Historical explanations don't present or even presuppose any account of how mathematicians are in connection with mathematical reality. They describe the ways in which mathematicians do something, namely, modify their symbol systems. So let's look at a wonderful example of this, about which quite a lot is known. The 19th century Irish algebraist Hamilton went on a long hunt for things he called quaternions. We don't call what Hamilton discovered any kind of number anymore. Hamilton's insights got him absorbed and reclassified in abstract algebra in the early 20th century. After Argonne showed how you can represent complex numbers geometrically, Hamilton took a further step. He realized that complex numbers could be treated as ordered pairs of real numbers. And so he asked himself, can you generalize that to higher dimensions? And quite quickly, he saw that 3 dimensions looked pretty unpromising. But 4-dimensional reals, a quadruple of reals, looked much more promising. And so he said, I want to find a 4-dimensional version of the real numbers, just as the complex numbers are a 2-dimensional version. He called them quaternions. And he wasted a lot of paper in looking for them. He spent years trying to define a multiplication table for quaternions. He would go into his office. This may be apocryphal, but it's a lovely story in the morning. And he'd come out at lunchtime or in the evening, and his wife would say, have you discovered quaternions yet? What did she mean by that? Do you yet have a multiplication table? So he scribbles away in his study various kinds of multiplication tables, and none of them work. And so they all go into the wastebasket until one day, walking through Dublin, he's got the problem in his head. I mean, he's got the symbols dancing in his head as he walks around. We all know how that works, I think. How, you can be absorbed in a formal problem and, you're just thinking about possibilities in the way I suspect chess masters think when they're playing chess. It's common across a number of domains. Anyway, it came to him, and he carved with his knife in the stonework of a Dublin bridge the crucial element of the multiplication table. Okay, that's one example, but I'm going to give you another one. The discovery of complex numbers, because it brings out something that is, I think, very important and very useful in thinking about mathematics and mathematical truth. As you probably know, quadratic equations were solved by the Babylonians. They didn't have algebraic notation, but they could solve problems that we think of as being quadratic equation problems. Renaissance mathematicians inherited these techniques, and they tried to solve cubic equations. And some of them knew how to solve cubic equations, some cubic equations. And they developed methods for doing this, again, without algebraic notation. And the methods sometimes led them to expressions involving the square roots of negative numbers. Now, introducing these numbers seemed, in the words of the English translation of a famous paper, subtle and useless. And the reason for that was because you could only figure out how to make sense of the expressions involving the square roots of negative numbers if you already knew the root. And the method was, of course, supposed to give you the root. So it was useless. From the late 16th century to the early 18th century, complex numbers were on the fringes of mathematics. They were used by some people on some occasions, but they weren't really a fixed and definite part of the mathematical corpus until there were clear pragmatic advantages. And those started to accrue during the 17th century as these so-called imaginary numbers were useful for solving some higher degree equations, particularly quartic equations. But then in the early 18th century, Euler recognized that if you substitute this, I is the square root of -1, iz for x in the series representation for e to the x, you obtain something which can be written as the cosine of z plus I times the sine of z. So there's this really strange and unexpected relationship between exponential functions and trigonometric functions mediated by imaginary numbers, or complex numbers as they came to be called. And if you substitute pi in Euler's formula, you get what Euler called the beautiful identity, that e to the I pi is -1. So it's when these numbers start to look useful, when this notation looks as though it has a purpose, that you begin to get acceptance, full acceptance of them. None of this looks very much like discerning a new bit of mathematical reality. It looks far more like developing systems of notation and using the ones that have a point, that have some significance in solving problems, and ignoring the ones that don't. So here's an obvious proposal. Give up descriptivism for mathematics, abandon the Tarskian correspondence theory. Suppose that the function of what we call truth, or truth-like notions like accuracy, is constant across all domains, but that the structure of truth may vary. That sometimes truth, as in the factual domain, is a complex mixture of pragmatic and correspondence components. And in other cases, truth has nothing to do with correspondence at all. So here's an account of truth and progress in mathematics. Truth in mathematics emerges as mathematicians progressively extend their symbolic systems, so that what count as the truths are the formulas that can be reached by following the rules of progressively stable systems. Mathematical progress is pragmatic progress, solving problems and overcoming limitations. Now, I want to give you, just at this point, a footnote to my story about Hamilton and the Quaternions, because it turns out that although Hamilton made this progressive advance in developing the multiplication table for quaternions, it all got reconceptualized. His system didn't turn out to be progressively stable. It was a stepping stone to the abstract algebra treatment of things like groups and rings and vector spaces. It's a step towards something different, but it was a progressive step in that. Okay, so if we're going to talk about problems and limitations, as I said yesterday, anyone who talks about pragmatic progress owes an account of problems and where they come from. So I'm at this point going to turn, and I'm delighted to be able to do so, to the philosopher mathematician for whom this lecture series is named, Descartes. In the 17th century, as Descartes knew very well, only a handful of locus problems could be solved. People knew how to solve the problem of what you get if you have two strings, a string attached to 2 points and a pencil, and you put the pencil sort of up against the string and you go around like this. What you'll get is an ellipse with those two things as foci. But many locus problems, most locus problems, could not be solved. And Descartes, building on the achievement of Viette in developing a notation for algebra, invented coordinate geometry. He does it in the Géométrie, and it's brilliant. And as he points out, he has solved problems nobody previously had dared to attempt. So classic locus problems can now be formulated algebraically, and when you formulate them algebraically, they can be solved. Terrific. And that leads directly into two other great 17th century problems, which are the problems of constructing tangents for curves and finding areas. And Newton comes along and not only takes up these problems, but he also makes a connection with motion. He thinks of curves as dynamic entities. He thinks of them as swept out by the motion of a point. And in developing the calculus, he simultaneously solves the geometrical problem and he paves the way for analytic mechanics. Of course, the calculus is also developed by Leibniz, and in the algebraic form that Leibniz gives it, it then becomes more useful in 18th century mathematics. So, two different ways in which problems gain significance. The Descartes contribution, the Cartesian contribution, you show how to solve generally something that can only be solved in particular cases. So there are some problems, and you can answer a few of them, and Descartes shows how to give a general method for solution. That's often a way in which a mathematical problem comes to be seen as significant. Another one, you develop tools for inquiry. You give the sciences something that they can use in the description of nature. But there are other sources of significance. Remember Euler and the beautiful identity. The connection between trigonometric and exponential functions was just too lovely. We have to have that as part of mathematics. Or there are considerations of play. John Horton Conway, famously working on the theory of cellular automata, invented a thing called the game of life, which so infected the Cambridge mathematics faculty that the model for this was a series of tiles spread out over the hallway and down corridors and into offices and all over the place. And then there are apparently uninteresting or limited questions that turn out to have enormous benefits for solving other problems, as when Pascal responds to a problem of awarding money in an unfinished game, or when Euler thinks about why you can't traverse the 7 bridges of Königsberg without retracing your steps. All of these are distinctive ways in which mathematical systems get to be hailed as significant. But where do the original problems come from? Well, I've talked about problems coming from the mathematical past. We have ways of doing something in special cases, nothing more general, of the needs of sciences, and aesthetic pleasure and fun. But all of that happened in the history of mathematics, and it changed the status of mathematics. From the early modern period, mathematics has been a high status discipline, a higher status discipline than philosophy, say. And that's because it's earned recognition for supplying resources for inquiry. So it's as if the community of inquirers said to the mathematicians, go and do the kinds of things you like to do. And, from time to time, we'll probably be able to borrow some of the things you give us. And that's turned out to be a very good bet. It's a good strategy for general inquiry to let mathematicians play with their symbol systems. But I want to go way back to the origins. Again, genealogy. For a very long time, really from the time of the ancient Babylonians and Greeks up until the Renaissance, there was very little extension of mathematical fields. To be sure, there were complex problems within those fields that needed to be solved by accountants, by engineers, and so forth. But there were no really large new developments in the fields themselves. Now, those elementary branches, arithmetic and geometry, were surely generated by practical problems that extended back, I think, into our prehistory. I think before we have written documents, people were already doing arithmetic and geometry. Symbolic systems were useful in everyday operations, matching groups of things, tallying, measuring land, and so forth. And for centuries, really, as I say, from maybe the 5th century before the Common Era up through the Renaissance, it wasn't obvious how extending these systems in any way would be valuable. So, some conclusions. First of all, non-descriptivism fits the history of mathematics. It explains the changing position of mathematics among fields of inquiry. And it also explains the apparent apriority of mathematics. The mathematicians are in control of the rules, and they set up systems to have those rules. And so, you just don't deny those things until something comes along, and then you change the system. As, for example, Renaissance mathematicians did when they gave up the idea that you couldn't have square roots of negative numbers. Okay, now logic is, I think, a special case of this. Most of the history of logic, I claim, consists in the development of what I call semi-formal systems. Individual laws like the law of non-contradiction, syllogisms, rules for non-deductive inferences. Those are tuned, in part, I think, to figuring out how to do inquiries of various kinds, and they're also attuned to settling various kinds of disputes. There are partial anticipations by Leibniz and Boole, and then logic becomes a fully formal system in 1879 with Frege's Begriffsschrift. So I think the roots of all of this are in efforts to figure out how to do research, how to make inquiry, how people should proceed in trying to discover answers to the questions that concern them, and how they should resolve disputes, particularly, I think, in courts of law. So it's investigation of the world and figuring out human social life. And I don't know which of those is more important. There were links to mathematics, surely, before the development of fully formal logic. It was assumed, for instance, that the tools for everyday inquiry should be used in mathematical proof, that logic would apply to mathematical proofs. And in the historical development of mathematics, puzzling cases emerged. There were theorems that were apparently proved that faced counterexamples. And that inspired developments within logic. So the 19th century development in logic is in part, I think, fueled by the fact that there are results, apparent results, that depend on an illegitimate switch in quantifiers. So formal logic responds to this need, responds to the need for more precise methods of proof. You can find it not only in Frege, but also in some of his contemporaries. Dedekind, Peano, and Hilbert are all trying to do something very similar. And they do so by treating logic as a mathematical system. And after that, logic makes further progress. Before, logic made progress pragmatically by improving the tools for inquiry. And afterwards, we've expanded the formal system that Frege had and systems like that to help with other forms of inquiry, particularly by bringing in to the scope of logic parts of language that Frege left out. So I think, for example, things like modal logic, deontic logic, and efforts like that of Davidson and some of his successors to try to regiment various bits of language, adverbs, adjectives, and so on and so forth. But also, once logic is developed as a mathematical system, it raises mathematical questions. And increasingly, logicians show up in mathematical departments as people who pursue the kinds of mathematical problems that arise about any kind of formal system. And logic in particular. So that's an account of logical progress. Logical truth, then, is a species of mathematical truth. The logical truths are the theorems of progressively stable systems of formal logic. So as to sum up, we don't need the myth of the a priori. We don't need the myth that there's an abstract realm for mathematics and logic to describe. Then these are non-descriptive fields. Logic and mathematics aren't illuminated in any way, I think, as characterizing them as a priori. They belong to unusually stable traditions that have found ways of making some of their elements appear obvious, most particularly by setting up these systems with carefully defined rules. And until you change the system, the rules are, as it were, in control. And so these things are not to be given up. But as Quine, as Mill, and as Dewey, I think, all saw, that's not the end of the story, because the history of mathematics shows that these systems can be given up, usually by absorbing them in some different, some larger, some more useful, some more encompassing system. Thank you very much.